Welcome you all. This is the 15th talk organized by Istanbul University Observatory. And today our speaker is Tomaso Belloni. Let me introduce him with few words. He's from Italian National Institute for Astrophysics Astronomy Observatory, INAF. And he currently works in Southampton University as a visiting professor. His main interests are stellar mass black holes, X-ray binaries, neutron star binaries, cataclysmic variables, time series analysis, etc. And he will give us a talk titled Fast X-ray Variability and General Relativity to us. So we thank Tomaso Belloni for giving this talk to us. Please, it's your turn, Tomaso. Thank you.
Thank you, John. It's too bad I cannot be there, and these times it's difficult to travel. I just want to correct one thing. I'm not really at the University of Southampton. I'm a visiting professor, but I'm not visiting since a long time because of known reasons. So I still get this this title, but it's not really visiting right now. And so what I will talk about is the fast variability and general relativity. We have been working on this for quite a long time, and we think that there are very good measurements now that can go into general relativity effects from X-ray binaries. It's not really very recognized by many people, and but it's a parallel way to get to elusive things like spins of black holes and relativity effects. And just as an introduction, this is an X-ray binary in a very nice image by Bob Hines. And what we're talking about is something that happens well within the inner pixel at the center of this accretion disk. The system is, as a whole, very complicated, and this accretion disk is something that we don't really understand completely. We do have models, but it's clearly much more complicated. And so this leads to a major problem in the field. The thing is that what we are trying to do is to measure GR effects in a strong field through accretion, but we don't understand accretion very well. And accretion is modified by general relativity. So we also would like at the same time to understand accretion using general relativity. And this is a snake eating its tail. We need to get out of this problem. And if you look at the plot on the right, which was published many years ago by Dimitros Psaltis, you see the potential and the curvature of a gravitational field, and you see where different objects are located. You have the Earth here. There's white dwarfs. Sagittarius A star, which became very famous in the past few days. AGN have a very strong potential, very close to the horizon. You can get very close to the event horizon. The same is for intermediate mass black holes if they exist. Oops, sorry. But X-ray binaries are the best laboratories because also the curvature of the field is maximum. This leads to the very often quoted effect that you're going to get torn by black hole if you fall into it. If it's an X-ray binary, while you stay alive for a while more if you fall into an AGN. That is the bad part of the X-ray binaries. The good part is that we can study very curved space-time. And you can get gravity from many experiments. This is a very complicated plot that has on the left side weak field, on the right, on the middle side strong field, and then you have a strong curvature on the top, a weak curvature on the bottom. So if you want to study very weak fields, you have the lab and you have cosmology. Weak fields, strong curvatures. Weak fields, weak curvatures, solar system, binary millisecond pulsars. Gravity is actually checked there very well. If you want to have weak curvatures, as you've seen, you go to the galactic center to M87. You have the Event Horizon Telescope. There's not a real image because this is an old slide. But then if you want to have strong fields, then you have to go to accreting binaries to get strong curvatures. Then if you want to have dynamic spacetime, then you have to go to mergers, GRBs, gravitational waves, and in case of weak curvatures, then you have to move to the LISA mission that will come in a few years, and things that you can do with radio pulsars. So you can see that the square where we want to get here is this one, strong curvatures, strong fields, and that contains accreting binaries. Some of the new missions I had in this slide are actually current missions. Now, if we didn't know anything about black hole binaries or X-ray binaries, and we wondered what characteristic timescales you have in a system like that, whether you have a black hole or a neutron star accreting, then you have two types of frequency, of timescales. One is on the right, it's accretion. Matter is accreting on the black hole, so you can think of important timescales like the radial light crossing time, the radial sound crossing time, the free fall timescale from a certain position, the viscous timescale at which things propagate, viscous propagation in the accretion flow, or thermal propagation of differences in temperature. But you also have GR effects, and you have object effects. If you have a neutron star is spinning, might be spinning very fast, and so you might detect, and you do detect, the rotation of the neutron star. You also have frequencies related to gravity. One is the Keplerian frequency of anything, and if this anything is orbiting, it can also have a periastron precession, and it can also have a Lense-Thirring precession if the central object has a spin. So you have all different time scales, and you wonder, you know, I'm interested in the left ones right now, although the right ones are very interesting. How do I tell them from the others? And this is where the problem comes. I wanted to make a plot, so I went to a theoretician friend. I went into his office, I closed the door, and I said, now you give me the radial dependence of these time scales for an object. And then he started saying, well, it really depends, you know, the pressure dominated areas. I said, no, just give me time scales. He didn't want to. So metaphorically, I just grabbed his ankles, pulled him up, and just started shaking until these time scales came out. And he gave me these numbers. As a function of gravitational radii for a 10 solar mass black holes, under a list of infinite caveats and assumptions, which I conveniently forgot. These are the timescales. The gravitational ones are the dark ones, and the light ones are the accretion ones. You can see a viscous timescale at the top. You can see a sound crossing timescale, thermal timescale, free fall timescale, and then you have the three relativistic frequencies. There are 4 plots because one of them is the difference between 2 of the other ones. And what you can see here is that if you exclude the top one, these ones are in the same range. And annoyingly, many of them seem to be going up at the same slope as the Keplerian one. So if you see a point, just a number, a time scale, a Y number, then you have to place it here. And you really have to know the radius very well, which you don't, to identify this frequency. And the slide that I skipped gives you the range of these frequencies. Keplerian frequencies around an object are in the range between 100 and 1,000 hertz. And then you can do that in different ways to measure, try to measure the spin of a black hole. You can do it with timing, and you can do it with spectra. Then you have periastron precession. If your orbit is not circular, it's slightly slower, not that much slower. It's been tested. The periastron precession is tested by Mercury, of course. That was the first 1917 measurement by Eddington, and the double pulsar is measuring, as we speak, more and more precise values for this type of precession, and for that you need timing. And the Lense-Thirring precession, which is a frame dragging precession of an orbit which is not coplanar with the spin of the object, is much slower, 1 to 50 hertz. It has been tested for the Earth. There was a mission by NASA called Gravity Probe B that unfortunately did not work very well. So it's been tested with like 20% errors, which is a bit too large. The price for this kind of study is that you can get strong gravity effects. So you can prove the existence of black holes. you can measure the spin of a black hole and therefore prove the existence of a spin of a black hole. You can measure the presence of an innermost stable circular orbit, which is predicted by theory. And you can measure the precession frequencies in a strong field. So all these things are very, very important. At the time when we started this, the EHT results and the gravitational wave results were not out. So there were really no answers to these questions. Now let's see what we see in X-ray binaries. We need fast timescales, and there were clear frequencies that were observed in the 90s from neutron stars. You can see here a few plots where you see power density spectra, where frequency is on the x-axis and power is on the y-axis. And you can see that there are broad noise components, but there are clear frequencies. You can get a number here. This is a bit uncertain, but if you look at this plot here, I have no idea what this plot is, but anyway, there's a peak at about 60 hertz. And it's very clear. You can get, no matter which model you use, you get a very good number for that peak. Oops. Sorry. Again. Yeah. So, but these are too slow. You see, you want to see something buzzing and orbiting around a neutron star, and you expect it to orbit 1,000 times per second, not 70 times per second. They were called quasi-periodic oscillations, and they've also been detected years later in black holes. They're good for the precession, for Lense Thirring precession, but people did not even think about it at the time. They had very complicated models involving neutron stars and spinning neutron stars that eventually were proven not to work. We had to wait for 1996 when the RossiXTE satellite was launched to see high frequency things, mainly because they are weak. So you need to have very, very large collecting area. And then more interesting things were seen. In the black and white plot, you see two peaks in the power spectrum of a neutron star at 600 and 900 hertz. Now, these are the frequencies we are talking about, and there are two frequencies. The range goes between 300 and 1200. That, of course, can depend on the radius at which these things are emitted. They often are two peaks. You can see two peaks in that plot very clearly, and they move in frequency together. And they seem to keep about the same frequency separation of 300 hertz. We'll get back to that. If you are not colorblind, you can see that plot on the bottom where you can see time on the x-axis and frequency on the y-axis. The two frequencies are moving. The red indicates the peak, and they're moving up together. And again, there were models that related that to the neutron star spin. And as you will see, these models are not really going anywhere. So back to general relativity, there was a great idea in 1999 or 1998 by Stella and Vietri, who proposed that these peaks would be direct representation of those frequencies that I described before. One is slow, two are fast. So you can identify the fastest one with the Keplerian frequency, which is the fastest, is expected to be the fastest. Then you say, you take the slower one, the 300 hertz by slower one as a periastral precession, and the slow one, the previous one that we observed years before, as a Lense Thirring precession, all at a certain spatial radius, which nobody knows why it's spatial. And the nice thing is that this model didn't really work, but amazingly almost worked. If you look at this plot, this has the delta nu between the two high frequency ones versus the upper one versus the Keplerian one. The points are the gray and the black ones, and the model for a certain mass, essentially the only parameter is the mass of the neutron star, goes very well through the points. It completely misses the high frequency points, which is not a small thing. But it's amazing that this line is even close to the points. It's not expected to be. It could be anywhere else in the plane, and it's just what the points are. Now, this model has a very powerful point, which is just general relativity. It just gives you the three frequencies you can find on any GR book. That's a strong point. It also has a very weak point, which is it's just based on general relativity. So it tells you these are the frequencies if what you observe are those effects. It doesn't tell you how this thing is emitted. It doesn't tell you how you can orbit in an elliptical way, an off-axis way, in an accretion flow, in an accretion disk. It doesn't care. It was never complicated by them. It's just, these are the frequencies, you work out the rest. So you can, well, this is the same thing. You have Keplerian frequency, periastron frequency. Periastron frequency, you don't have to imagine Mercury. Mercury precesses by, I don't remember what, very small amount. Every orbit of Mercury is slightly shifted. But here we're talking about 1,000 rotations per second and 700 periastron precession frequency, 700 hertz, means that basically it's like a flower going around the neutron star. The nice thing is that, as I said, this plot works very well. The first plot only had the gray points, then the new points here were added in 2006 by Boutloukos, and it worked very well. And also, if you do a correlation between one of the high frequency, one of the low frequency, it is amazing how the slope of the relation is exactly what expected by theory. Unfortunately, it would be better if it was a factor of 2 off to fit very well the model, but it's still a very good result. And we did this plot years later, where you plot, we thought it is much better if you have 2 numbers. You plot one versus the other. You don't plot their difference versus 1, because that's a very unnatural thing to do. So if you do a plot of the upper versus the lower, you have a forbidden zone, which is where the lower would be higher than the upper, which is impossible. And then you have 3 lines here, which are 3 different neutron star masses for the same model. You can see it's very good, although these points seem to go at a different slope and go out of the plot. And if you do, sorry, this is an important plot because it's been updated with all the numbers ever published on these peaks. And there are none since a few years because XTE was the only satellite that could do it. And if you do the delta nu, you get this. This is a new version of the plot. Remember, these are different objects, so they don't have to have all the same mass. They can have different masses. And what I find amazing is that this plot the model makes 3 predictions. These curves you see here give you 3 predictions, very clear predictions. 2 of them are very obvious, and people always looked at them. The curve should go up at low frequencies, and it does. The curve should go down at high frequencies, and you don't see it here, but this is one source, and it does. But it makes a very strong prediction that you should not have separation larger than about 400 hertz, or depending on the mass that you want to take. So it has to be a limit on the delta nu. And if you look at the delta nu distribution, this is what you get from all those plots, all those points. This is a Gaussian. I don't know if it's a fit that's just been put there by hand, but it really looks very, very well fitted by Gaussian, peaking at 300 hertz. And you don't expect to have points here, and you don't have them. Of course, it would be very nice if there was a drop, and there isn't a drop. But there are no high delta nus. People have connected this to the spin of the neutron star for many, many years, and then we went and showed that there's no relation. This is the distribution of spins of neutron stars that we know in accreting systems, and this has no relation to this plot at all. So what if you go to black holes? Black holes are better objects. They don't have a magnetic field. They don't have a spinning neutron star inside. They have a spin, but they don't have like a surface which can give you a lot of nasty effects which are not related to relativity. And sorry, black holes are a different case. While for neutron stars, there are all these points here, many, many, many points. For black holes, there are very few. There are a few cases of significant detections. Many of them are actually insignificant detections reported as significant. Years ago, 10 years ago now, we did a reanalysis of the almost complete RELATIVISTIC archive. A few observations were missing. RELATIVISTIC was dismissed in 2012. And it was just done in an automatic way. So taking each observation automatically, no averaging, no doing clever things. So we didn't find some of these detections. And we only found 11 detections in 2 sources. These are the ones that you find if you just do a blind search. One source here, GROJ 1655, has 2 peaks. This one here, which is broader at low frequencies, and this one is at higher frequencies. The dashed lines are the peak values for all the plots. You can see this one moved. This one is only one case. And here you have, again, a broad one at low frequencies and a narrow one at high frequencies, which moves a bit, moves very little. Of 12 million seconds, these are the only detections. If you do things cleverly, you find a few more. Averaging different states or doing the right energy thing or averaging different observations, but not that more. So you have very few, you can see these are not really fantastic signals, not very fantastic plots. You have very few numbers. They're all in frequency range that is lower than the neutron stars. You see the upper one here you have at 450. There's the highest one. You never get to 1000, which is good because black holes are more massive, so you expect slower time variability in any case. There's only one object, one weird object, the GRS 1915 plus 105, where there are 51 detections. And almost all of them are the same frequency. This histogram shows you the histogram of detection. These two are probably not real. And most of the points are here between 65 and 70 hertz. The average is about 69, I think. And so there's one number here. This number is very constant, is say 69, 65, 70. It's been observed many years later by Astrosat, and the frequency also was in the same range. So you would say this is an evidence of ISCO. It has to be ISCO, and it's obviously the Keplerian frequency at ISCO. The precession frequency and the Keplerian frequency at ISCO are the same, so it can only be one. It cannot be. It cannot be because we know the mass of this black hole. We don't know the spin, but the lowest frequency you can get is for 0 spin. So let's assume this black hole has 0 spin. Let's take the mass, and you get an ISCO frequency of 95 hertz. So this is something else, but it's a very clear number. It's always happening year by year, always the same number. We don't know exactly what that is. So there are open questions. What are the frequencies we observe? And are they general relativity? Then another very important question is, what is the modulation mechanism? Because one thing is to have a frequency, one thing is to emit flux that is modulated by that frequency. We know it's not coming from a flat accretion, Keplerian accretion disk, because the energy spectrum is very hard. So they have to come from a broader region. Are the frequencies we see the same in neutron stars and black holes? It would be very nice that we saw the same thing in all systems. And what we need is a good data set where we can check these things. And we didn't have one for a long time until we realized that we actually had one for a long time. And there was one observation of GRO J1655 as the only source where 3 peaks have been observed at the same time. This is the power spectrum. It has a peak at, I forgot, 17 hertz. Completely forgot the number, 13 hertz. We'll see it later. And if you go to high frequencies, then you don't see anything in this plot. But if you zoom and do it, making it at certain spatial energies so that it come out better, then you have a low frequency one at 300 and a high frequency of 450. We've seen them before. But now they are together with a 13 hertz peak. Now we have 3. And then we can test the model, because the relativistic precession model says these frequencies are the 3 relativistic frequencies at a certain radius, spatial radius that we don't know. We have 3 frequencies, so we can solve the system and find what the parameters of the black hole are. 3 parameters. One is the mass, one is the spin. Black hole has only 2 parameters, but the third one is this bloody radius that is special for some reason. The frequencies we have are these ones. They have quite precise values for the number. It's 17, not 13. These are the equations. Somebody at some point told me there's a mistake in one of these equations, and I do not remember which one, and so it's lost. But you probably will not notice. So these are the good questions, the good equations. This is the Keplerian frequency is a function of radius, mass, and spin. And these are the 2 other frequencies as a function of the Keplerian frequency, radius, mass, and spin. To solve this system analytically was not possible at the time. Then my colleague Sara Motta found a way to do it, which was amazing. So we had to do it through numerically. And we found a solution. Actually, you find a solution for any three numbers that you provide. So this is not special. The way to visualize this is that you have spin and mass. In the spin mass plot, changing the radius at which the frequency happens gives you a line. And so you have three lines for three frequencies, and you just find the radius at which they all collapse into one point. And they do, as I said, this is obvious, they do it. We find a solution for a spin of 0.29 with a very small error, a mass of 5.31 solar masses with a very small error, and this spatial radius, which is not particularly interesting, but it happens to be 5.68 gravitational radii. Well, it has to be small, it better be 5 and not 1,000. Now, things become interesting because there is a mass measurement for this object. The black hole mass measured from optical data is 5.4 plus minus 0.3 solar masses. And it's the gray band here. So what we detect is we measure the same mass. And then it gives us confidence that our measurement is correct and also the spin is correct. If you have these things, if you have a mass and the spin of a black hole, you have everything. You own the black hole. So you can calculate everything, including the radius at ISCO with this beautiful formula. Perhaps this one is wrong and not the others. And if you do it, you get our ISCO is 5.03 gravitational radii. The frequency of the oscillation is 5.68. The radius is 5.68. This is 5.03. So just outside ISCO. There are things that you can test. There should be no frequencies above the maximum value. The maximum value is the frequency at 503 gravitational radii. If you measure anything that's above, then it doesn't work. High frequency QPOs, we only have few the same frequency, but the low frequency QPOs, which are called type C QPOs, move a lot. So you can make this plot. This is a plot that has frequency versus frequency. You plot the three frequencies, 1, 2, and 3, these blue points, versus one of them, the low one. Okay, so this point is 1, 1, 1. It's a trigger point. And these are the two that we base the model on. So once you know the black hole, you know the lines. This is how this one would move if it moved. This one is how the precession frequency would move. And this is how the Lense-Thirring precession would move. This is an obvious line because it's plotting something versus itself. And you have all these measurements, all these red points are measurements of QPOs, and they're all below. This one is at the limit. This is the range for the error, taking account of the error where these points can be. So they just stop here. You don't have a point here, which is very good. And also, if you take a power spectrum, this is a bit of a complication, but if you take a power spectrum, you have this beautiful peak, and this is twice its frequency. You also have these high frequency bumps. I'm working with this high frequency bump since 1988. And if you plot these two, they lie on these lines. So these are actually consistent with what I've been saying since 1988, that these broad bumps are giving you the same frequencies as QPOs. You only have 2 points here. If you want to look at by eye, you can actually say this is just a line going up like this. You can, of course, it's allowed. But it looks like things are now getting together. You can do more than this because you say there's a spatial radius at which this emission comes from. But you don't see deltas, you see broad peaks. Why do you see a broad peak in your spectra? The easiest way out is that you just jiggle this radius. Your radius is 5.68, but it's not exactly 5.68. It moves a bit up and down, and then your frequency moves a bit up and down, and you make a broad peak if you observe for an hour. But then you have to check whether this works, because these three peaks have widths, and the widths are not the same. And you know the frequency, you know the functions that I showed you before. So if I jitter a bit the radius, do I reproduce the exact width of the three peaks? That's kind of a fingerprint. And it turns out if you jitter the radius between about 2%, is sufficient, and you recover the width that you observe in the power density spectrum, which is also very good. Now, this leads you to compare your spin with the ones that are measured in other ways that I will not mention here with energy spectra, and we don't really fit. I don't know if there's new measurements here, but we get 0.29, and they all get high frequencies. We'll get back to that at the end of the talk. So we don't agree with other measurements, but so what? You know, they have to prove that the measurements are better than ours. This proves that we cannot be both right, but it doesn't say who is wrong. Unfortunately, this was the only observation that was available, and XTE was decommissioned and then re-entered the atmosphere, unfortunately. So we don't have an instrument to do that anymore. And the new instruments that we show at the end are not good for doing this kind of study. So we don't have anything new after that. However, since now you are sort of confident that the model works, you can lower your standard and go to another source. The other source that has high frequency oscillations, XTE J1550, has only 2 peaks simultaneously, the low frequency one and one of the high frequency ones. So with 2 numbers, you cannot solve a 3 unknown equation, a system of equations. However, you can now put in the mass measured by optical people. And in that case, you don't get the mass, you don't get consistency, but you can measure the spin. And that's what we did next. There's this observation where you have a beautiful peak at 13 Hertz. That's why I remember 13 before. A beautiful peak at 183. Then you have this peak, which is annoying, but it's been shown in a huge different paper that this is something else. So we have to take these 2 numbers, 13.08, small error, 183, small error. Now you only have 2 lines. You use the mass. So you only have radius and spin now. They cross. Spin is 0.34 plus minus 0.01, and the radius is 5.47 Rg. The mass that we used, we did not derive it, is 9.1 plus minus 0.6. So there's no internal check, but we get the spin using the model. We do the same plot as before, and again, all these red points stop right where you expect the maximum, and the high frequency bumps that you see sometimes lie on the lines that you expect from the model. This is really very encouraging. You do the jitter game as we did before, and it works, although you have to do 5%. It's important it's not 80%, because you cannot jitter the radius by huge amounts. And at the time, I don't know now, our value was broadly consistent with the competition, although the competition had very large errors, so it went from 0.29 to 0.62, so it contained a lot of numbers, a lot of values. If it's a relativistic effect, these oscillations should have an inclination effect. Systems are inclined randomly in the sky, of course, but if you have things that are observed edge on, your orbit is edge on, you expect to see differences than you see it in front. Actually, if it's completely face on, which is an almost impossible situation because it's very, very precise, then you don't see anything, because anything is orbiting in the plane of the sky. It doesn't give you any effect. And this is a very difficult thing to do, but if you look at the left plot, you see averaging, the red points are averaging the low inclination sources, and blue is the high inclination sources. Is a function of frequency. So the high inclination sources have on average a stronger, this is the intensity of the oscillation, a stronger oscillation than the ones which are at low intensity. And that is broadly consistent with what you think. This is not important. Then a more realistic model came. I only have this slide to show it, but Adam Ingram in the UK started to do a bit more. He concentrated on the Lense Thirring precession, leaving the high frequency ones apart. And he built this model where it's actually, of course, there's, if you have this inner region of the disk that precesses, that you can see there is flying saucer in the middle, each radius will precess at a different frequency because precession depends on the radius. However, observationally, essentially, you have the effect of seeing an orb, a precession torus, like the one you see in this plot. And then you can do some more predictions. For instance, you can see the colorful disk. The disk reflects the X-ray emission coming from the torus, and depending on the position of the torus, you have different effects. And this is an effect that you can measure and has been actually measured. And this goes together with the truncated disk model that came from originally from the same group, which explains the energy spectra by positing that there is an inner part of the disk, which is in a different state and gives you a hard emission, which is what you need for the oscillations. So these two things go very well. So yes, they go very well together. It's only the low frequency one. It adds complication, but it's a very good complication because we're getting to the right ones. Now the problem is, as I said, that our beloved instrument was killed. It was actually killed because it was working well, but NASA decided to kill it. Even though we wanted to pay for it, we meaning everybody else besides NASA, they decided to switch it off. And in order to prevent the Chinese from hijacking the satellite, they intentionally mispointed it so that the solar panels would not get energy and the instrument would really die. And then it re-entered. Since then, we have new instruments, and I listed here the three main ones. AstroSat is an Indian satellite that I'm involved in. NICER is a NASA mission on the space station, and HXMT is a Chinese satellite. Unfortunately, the beauty of RossiXTE is that we had a very large area, very good. We had a very good range of energies because we had high energies, which is where these things are stronger. And we had a satellite that we could point anywhere we wanted, anytime. There was no problem. You could call them up and say, there's a beautiful thing to see. And if you convince them, they would just turn the satellite right away and observe for you. Or they observed every day a target for 5 years. Now we have AstroSat. AstroSat is similar to RossiXTE. It has very good collecting area. It has the same energies, even higher. But it doesn't have the same strategy. AstroSat is like an elephant. In order to move AstroSat, it takes a long time. In order to convince them to move AstroSat, takes a long time. So what AstroSat does is not the same thing. It takes very long observations of targets, which is good, but it's not for this, because we want to observe at a certain time only when we think these objects are doing something. Then we have NICER on the space station that has a very nice area. It's very, very flexible like XTE. Unfortunately, it covers low energies and has very, very puny area at high energies. And then the Chinese satellite has a strategy. Essentially, they observed anything that's interesting as much as possible. So it's good. And their idea of what is interesting is the same idea that I have of what is interesting. It has good energies because it has 3 instruments covering low, middle, and high energy. Unfortunately, it's small. So if you look at this table, it's quite depressing because you almost have what you had before, but you don't. What we've been doing so far was to try to emulate XTE. So say, take NICER, yeah, the energies are too soft. Let's throw away 99% of our photons and be left with a tiny instrument that observes about 10 keV. And that's not a very, very positive strategy. You have to use what you have in its best way. And that's what we did. This is an observation. These are observations of MAXI J1820. That was a very bright source a few years ago. And we observed it. I mean, they observed it. We used the data. This is the power density spectrum. There are many power density spectra like this. It has a very nice peak. It doesn't have high frequency PPOs. We never see them in NICER. But it has these bumps. I showed you these bumps are the low frequency extension of the high frequency oscillations. So why don't we use these ones? This is the time evolution for about 70 days, 80 days of these frequencies. And you can do the same game as we did before. And Yash Bhargava, PhD student, then PhD student in India, did this. And you get the same plot. This is 1-to-1, so it's a trivial plot. Then you have the 2 bumps as a function of this one. And you can find a solution for this, just using the bumps, no high frequency oscillation. The optical mass is 8.48 solar masses. And if we use that optical mass, then we get a spin for the object. And the spin for the object is 0.8 with a very, very small number. So it's a higher number than before. You have to consider that this is a bit of a tricky measurement because these are broad peaks. Broad peaks mean, first, it's not that obvious how to determine the peak of the broad peak over noise, but that's a small thing. The other one is that if you take the Ingram model, then you have that precessing torus. The torus is big. If the torus is big, things become a bit more complicated. You cannot really use just the Lense Thirring expression from relativity books. Things are a bit muddier. So the precision, the error of 0.016 in the spin is not exactly the one that we have. Really, we need to add something there. So it's an idea that it's spinning at a faster spin. And then you can always go back, and Saramotta went back and looked at XTE data, and at XTE J1859 plus 226, it's a very old source, beginning of XTE. The mass is not known, but she found 3 peaks. The 2 high frequency peaks are not really fantastic peaks, but they are significant. In this plot, perhaps the high frequency one is not significant. There's one observation where there are 3, the one that you see in the plot, and there's one observation where there are 2 peaks. And then we can play with that, doing also simulations. And what you get is the same plot, you know this plot, right? High frequency ones are here. This is the range, it's now pretty large, of allowed ISCO. And these are the high frequency ones. These are probably 2 bumps that you found somewhere. So you find a mass of 7.85 solar masses. We don't have any optical mass, so we don't know if this is in agreement or not. And a spin of 0.149 plus minus 0.005, which is the most precise so far that we have found. And it's again a low spin. So this is probably the last one we can get out of XTE. Now these are the spins that we find. They are a bit low. If you look at the measurements from spectra, they tend to be much higher numbers. Often maximally spinning very close to 1. 1 is the maximum spin. That's also a prediction by general relativity that you have a maximum spin. And you also have gravitational wave sources now, and whenever they see the collapse of 2 black holes, they can measure the spin of the 2 objects. They cannot measure it very well, the spin of the 2 objects. It's projections of the spin on the plane of the sky, so it is not that clear. So I try to compare the numbers in a more quantitative way. I cannot show you the comparison with the gravitational wave sources because I was promised the numbers, but I didn't get them in time. So I don't have those numbers, but I have the numbers of the spectral ones, and these are the ones. This is the source number, forget it. This is the black hole spin. The red ones are the measurements done using spectra. The triangles are values of lower limits, so they're above. The maximum is 1, so this plot probably should have been 1. The blue points are the ones that correspond to a source for which we also have a spin. This is the histogram, and these are our 4 numbers. So these 4 numbers, of course, they're only 4 numbers, but they tend to be more concentrated at low spin than at high spin, like the spectral ones. And there seems to be clearly a difference between the values that we find and the values that they find. However, I cannot show you a plot, but I can tell you that the gravitational wave measurements also favor lower spins. And talking to people who are trying to reconcile values, they have a serious problem. I haven't seen any calculation, but they're just talking. What they say is that if you take high spins, if you take these values here, which are very high, then you need to slow them down before they go into merging and are detected by gravitational waves. And what they find is that anytime they try to slow down a bit the black hole spins down to zero. So for them, it is very difficult to slow down a highly spinning black hole to a low value. So they're very happy that we see actually lower values, because then they don't need to slow it down. They just add that spin. We need more instruments, and I will show you a couple of ideas for future instruments. One is EXTP, the Enhanced X-ray Timing Polarimetry Mission. And it's a collaboration between China and European countries, where Italy has a big involvement. And that is, of course, would be the best that we can hope for. It's a 3.4 square meters at 8 kV instrument. If you look at the picture, it's a bit confusing because you have a lot of solar panels, but these are the solar panels. These two bars of chocolate in black are the instrument itself. And the other yellow ones are sunscreens to avoid sun radiation. Plus, there are telescopes here on the main body of the satellite. But essentially, it's two giant arrays of semiconductor detectors, very, very thin. RossiXTE had proportional counters. There were huge vats of gas. Astrosat has the same, very, very heavy. Half of the whole instrument was collimator, extremely heavy. So it was impossible to go to a very large area. Now they make these instruments, which are silicon drift detectors. They are 10 by 10 centimeters, and you can put them side by side. They're very thin, including electronics. So this is a fantastic way of doing your instrument. And you can see the areas here. The XTE one is the blue area, and the EXTP is the red one, the big instrument. There are other instruments. And you can see, of course, whenever you want to show that your instrument has a much larger area than others, we plot a limb plot. While if you want to show your instrument is not that bad to plot a log plot. But in this case, you can clearly see there's a difference. It will have a coverage between 2 and 30 kV. And you can see here a couple of simulations where you can see in time frequencies moving based on, I don't know which model. And here is, again, the radial epicyclic frequency as a function of precession frequency with very high value. The problem, of course, is that we have to do this, and there's a lot of work being involved in the XTP, and hopefully collaboration with China will be successful and will continue, and we'll be able to launch this. But it will take quite a few years before an object like this is in orbit. And of course, we're going to see many other peaks in the power density spectra, in addition to the ones we see now, but the ones we see now are the strongest, and that, of course, we know already. So you're going to see something like this plus complications. And this is another possibility. That's the kind of competition. It's Strobe X that has not even been proposed, as far as I know. 3 instruments, but one of them has a large area. One is a wide field monitor. I didn't mention it, but the wide field monitor is also here. What is important for this kind of studies is to detect transients. So if you don't have a wide field or all sky monitor, you're completely dead. There's no way you're going to see a shooting star if you look into a telescope. You need to have a naked eye to see the shooting star, and then a telescope to follow it up. And so everybody wants to have an instrument like that on their mission. And now there is the MAXI instrument on the space station from Japan that is doing this job. And on the space station, they also have NICER, and now they have a new system which connects. It's a laptop on the space station that connects the MAXI and NICER, so NICER can observe automatically when MAXI detects something. It's one of the beauties of being on the space station. So we're talking about an instrument that has the same name as the one on the XTP, Large Area Detector, LAD. I proposed to call the wide field monitor LAS, Large Area Sky Survey, but they didn't understand what I was talking about. But you can see the areas here. Here they made the mistake of making the area in log space. So it doesn't look like that much bigger, but it is much bigger. And of course, the high time resolution. So once we have one of these two instruments, we would be able to go forward. Right now, I think what we need to do is go back to what we have and try to build better models for the emission of these frequencies, because with the current instruments, as I said, we're going to see low frequency oscillations. We see them because they're very strong, very clear, very obvious, but we're not going to see high frequency oscillations. It would be very, very likely. From that GRS 1915 plus 105 source that had 51 detections in XTE, there were detections by AstroSat. As I told you, they were in the same frequency range, so not that much has been added. We did see variations with energy and with the spectrum, so there's a bit more than you can say about that, but not that much. And then if you look at, as I said, NICER is very, very flexible. You can look anytime you want. So you can look exactly when you expect to see one, but you don't have the energy range to detect it. AstroSat has the energy range to detect it, but the chance that AstroSat observes at the right time is infinitesimal. So it's frustrating, but we have almost what we need in all different missions. But still, we are working on a lot of associated things to try to strengthen the case. And if our first detection is proven, not the detection, but the model. So our first spin measurement was done with timing in 2014. That has proven the general relativity works in the strong field regime, that black holes exist, that they have an ISCO, and that they have a spin. That would have been the first measurement before all gravitational waves. Unfortunately, it's only 3 numbers, and it is still possible that we got this just by chance. So purely by chance, we take the model, put it into the data, get out numbers, and we find the right mass for the black hole. It is not inconceivable since we only have one case, and it is to date the only case where we also can get a decent mass out of it. So we'll need a few years, and then hopefully we'll be able to prove that these models are the right ones. And with this, I thank you, and I finished.
Thanks a lot, Tomaso, for this very nice talk. I'm sure there must be some questions from audience. Yeah. Mehmet Ali Alpar. Mehmet Hocam, buyurun.
Yeah. Hi, Tomaso. It's very nice talk and great to see you here.
Oh, now I see you. You were too dark.
Well, I'm against you. Yeah. Okay, it's great to see you. And I enjoyed the talk very much. I have one question about the widths of the QPOs. You associated that with radius jitter. If you instead try to associate it with the size of a boundary region in some accreting structure or some damping times, would the numbers make sense in terms of accretion?
The first one, if I understand it right, yes. The second one, no, because we have shown that it cannot be a lifetime effect. Okay. So it cannot be a damping. The reason is that there are, if you have an oscillation, you only have 2 things of the oscillation. You have the amplitude and you have the phase of the oscillation. Mm-hmm. But if you have a sinusoid, you only have what's inside the sinusoid, what's outside the sinusoid. It's normalization. And in principle, you can make a peak broad by modulating amplitude or phase, therefore frequency. So like your radio transmission works the same way. And there's no way to know if you have a broad peak, which one it is. Yeah. However, in many cases, as I've shown quickly, there are more than one peak. So this oscillation is not sinusoidal, and you have a first overtone at higher frequency, at twice the frequency. In that case, if you have two peaks, then you can tell if it's frequency or amplitude modulated. Because if the amplitude, the frequency, sorry, the amplitude modulation is the same for all peaks. Everything is broadened the same way. So the width of the peaks should be the same. If you modulate in frequency, then you say you modulate by a factor of 2, the upper one will be modulated by a factor of 4. So the relative width will be the same. And we see the relative width being the same. So we know that it is not broadened by amplitude modulation, therefore a damping cannot, it can be there, of course, a damping, but it doesn't have to be, it cannot be the main effect.
Thank you.
Is there any other question? There's a question in the chat, so
Yeah,
I will ask. Yeah.
How about comparison of model involving particle dynamics with model involving fluid dynamics to address origin of QPO? Wow. I don't know. It's a complicated question. It's a bit too generic to answer a question like that. I stress that there are two problems. One is where the frequency comes from, and the other one is where the oscillation comes from. And recently, there have been models by the group in Groningen, by Mariano Mendes and his collaborators. They have a model for how to explain what you see. They say, well, there is an oscillation somewhere, some parameters are oscillating. We have no idea why they are oscillating, but if they are oscillating, this is what happens. So it's the opposite of the relativistic model. They take all the rest and they ignore the origin of the oscillation. And then there's been a very interesting paper recently by, I forgot who the first author is, by a Greek group, including my host here, and then we'll have to talk about it, about generation of these frequencies without really the need of a Lense Thirring or relativistic frequencies. So how a system can start generating frequencies on its own. And that's something that we really have to get into now. It's not clear that the relativistic frequencies are the solution to the frequency part. There can always be another model coming up, but definitely how to produce this oscillation is not easy. You know, if you take a light bulb and rotate it, you don't make any change in the light curve. Then you start talking about Doppler effect. Then you start getting into something, but then you have to compare this with the observations. And what we have, many cases are not minor things. You can have something that has 20% RMS in the oscillation only. So it's not something you can ignore. It's really oscillating in your flux. It's not a tiny thing in your disk that's pulsing. You know, it's quite a major effect.
Okay, thank you, Tomaso. Is there any other question? It seems there is no any other question. So, Tomaso, we thank you again, and we also wish you to meet in Istanbul or in any other meeting physically.
Yes, absolutely. I want to visit again. What is it? Last time I was there in 4 years ago, 3 years ago.
Yeah, it must be 3 years ago. I was in Sabancı University. Yeah.
Yeah, but then 3 years ago, then something else happened, and we couldn't go anywhere.
Yeah. Okay, so thank you all for
okay, thank you.
Yeah.
Thank you for a nice talk.
So bye for now.
Bye.
Okay, bye-bye.